This is SpaceTime, Series 24, Episode 94. Coming up on SpaceTime, NASA's Mars rover comes up empty after its first sample collection attempt, the earliest moments of a supernova captured for the first time, and SpaceX builds the world's biggest rocket. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
NASA's Mars Perseverance Rover mission managers are working out what to do next after their first attempt to collect rocks and regolith drill samples failed to get anything into the collection tube. Perseverance, which is exploring Jezero Crater, is supposed to collect 43 samples from different areas, which will be placed into special sealed titanium sample tubes for eventual return to Earth. Perseverance's sampling and caching system uses a hollow coring bit and percussive drill at the end of its 2-metre-long robotic arm to extract samples. Telemetry from the rover indicate that during the first coring attempt, the drill and bit were engaged as planned. And post-coring, the sample tube was processed as intended, but it was empty. Images from the borehole showed the drill reached its planned 8-centimetre depth, but it encountered extremely powdery material, suggesting the rock was simply too soft. Of course, none of this is new. Previous Mars missions have also encountered surprising rock and regolith properties during sample collection attempts. Back in 2008, the Mars Phoenix mission sampled soil that was sticky and difficult to move into the onboard science instruments. That resulted in multiple attempts needed before achieving any success. And even Perseverance's near-identical twin Curiosity is drilled into rocks that turned out to be harder and more brittle than expected. More recently, the heat probe on the Mars Insider mission, known as the Mole, was unable to penetrate the Martian surface as planned. Perseverance is currently exploring 2 geologic units containing Jezero Crater's deepest and most ancient layers of exposed bedrock. The first unit, known as the Crater Floor Fractured Rough, is the actual floor of Jezero. The adjacent unit, named Ceta, which means amidst the sand in Navajo, has both Mars bedrock as well as ridges, layered rock and sand dunes. Recently, the Perseverance science team began using colour images from the Ingenuity Mars helicopter to help them scout out areas of potential science interest and look for potential hazards. In fact, Ingenuity's just completed its 11th flight, travelling some 380 metres downrange of its current location to provide some aerial reconnaissance south of the Ceta area. The 6-wheeled car-sized rover's initial science foray, which is slated to span hundreds of Martian days or sols, will be complete when Perseverance returns to its landing site. At that point, Perseverance will have travelled somewhere between 2.5 and 5 kilometres, and hopefully will have filled up to 8 of its sample tubes. Next, Perseverance will travel north, then west to the location of its second science campaign, Jezero Crater's ancient river delta region. The delta are the fan-shaped remains of the confluence of an ancient river and a lake within Jezero Crater, and it's a region which might be especially rich in carbonate minerals. And that's significant because on Earth these minerals can contain fossilised signs of ancient microscopic life and are usually associated with biological processes. And of course, a key objective of the Perseverance mission to Mars is astrobiology, including the search for signs of ancient microbial life. The rover will also characterise the region's geology and its past climate, helping to pave the way for ultimate human exploration of the red planet. And it will hopefully be the first mission to collect and cache Martian rock and regolith samples. A subsequent joint NASA-European Space Agency mission will send a spacecraft to Mars to collect these samples and then return them to Earth for in-depth analysis. This is SpaceTime. Still to come, the earliest moments of a supernova explosion captured for the first time, and SpaceX builds the world's biggest rocket. All that and more still to come on SpaceTime. Astronomers have for the first time captured the first moments of a supernova, the explosive death of a star. The never-before-seen observations reported in the monthly notices of the Royal Astronomical Society have recorded the initial burst of light, seen as the first shock waves travel through the star before it explodes. Supernovae are among the brightest and most powerful cataclysmic events in the universe. They mark the death of stars and briefly outshine an entire galaxy. Between them, stars and supernovae create almost all the elements on the periodic table, making them crucial for the evolution of the universe and ultimately life itself. The observations were originally captured by NASA's Kepler Space Telescope back in 2017. They show how the brightness of the light changes over time prior to the explosion. This event is known as the shock cooling curve, and it provides clues about what type of star caused the blast. Because the initial stage of a supernova happens so quickly, it's usually really hard for most telescopes to record this phenomenon. Until now, the data was incomplete and only included the dimming of the shock cooling curve and, of course, the subsequent explosion. But never the bright burst of light at the very start of the supernova. The new observations give astronomers the data they need to identify the types of stars that have produced other supernovae, even after they've exploded. Astronomers were able to test the data against a number of existing star models. And based on their modelling, the astronomers were able to determine that the star which caused this supernova was most likely a bloated old yellow supergiant more than 100 times bigger than the Sun. One of the study's authors, Brad Tucker from the Australian National University, says the data confirm that a specific stellar model known as SW17 most accurately predicts which types of stars result in what types of supernovae. He says the findings mean astronomers will no longer need to test multiple models to see which fits the observations best. SW17 resolves the question.
Yeah, this is the really cool thing because you're actually talking about a process that happens rapidly over a short period of time and is actually starting to become the mechanism of the explosion, what we call the core collapse, literally the core collapsing. You start to create such a dense amount of material that ultimately the pressure that props up the star can no longer balance out the gravity pulling inward. You have this battle between outward pressure and inward gravity. It no longer can withstand the gravity because it has so much mass building up that isn't really doing much. You therefore then start to build up too much gravity, therefore causing the rest of the star to implode. And that's really where the action starts. You start squeezing and collapsing the inside into a very super dense object, something we call a neutron star. But at one point, it cannot even collapse anymore. It can't create any more neutrons, squeeze any more neutrons, create any more dense of an object. So you reach this point, this breaking point, where you just release all of that built-up energy as a shock wave that then travels through the rest of the star, and that's actually what causes the star to ignite. So the end of the star is the birth of the neutron star, all within a short time period.
So we have this hydrostatic equilibrium ceasing. You've got gravity winning out. The star starts to collapse under its own mass, and eventually electron degeneracy reaches a breaking point. It literally can't crush any more electrons and protons together, and that causes a ricochet, a bounce back, and that is the supernova explosion.
Exactly, and it's that bounce back, what we call the shock wave, that causes the star to ignite. And seeing that shock wave is what we've seen with the discovery and led us to understanding the actual progenitor, because that's the exciting thing. Not only just seeing this awesome shock wave, which quite literally happens in the scale of minutes to hours travel through the star, but the length and the brightness of the shock wave, so how big or how bright the shock wave is and how long it lasts, is proportionate to the size and mass of the star. You know, how much pressure you build up is released by how much stuff is in there on the inside, and it allows you to directly measure what we call the progenitor star. What is the actual star that exploded, which is a really big effort now in supernova. What are the exact stars causing the exact explosions?
And this has never been seen before. This is the first time this has been done. How was it done?
So we've seen part of it before in what we call the shock breakout, when just the initial flash of the shock wave goes through. What we haven't seen in this case is the full shock wave traveling through everything, because again, once it releases, it travels through the star, and then the whole star ignites, and that shock wave actually goes off into space. And so we've seen little bits of it before. We haven't seen the complete picture go together, and this is what's happened now So led by my PhD student, Patrick Armstrong, using the Kepler Space Telescope. So this telescope famous for finding planets around other stars. Well, it takes a picture every 30 minutes. Now, that's good for finding planets transiting or going in front of their star. But in this case, it's good for seeing supernova and the first moments of a supernova. So using the Kepler Space Telescope back in 2017, we monitored tens of thousands of galaxies waiting for stars to explode, knowing that we would only capture a handful, but those handful we would capture in the first minutes, and we'd be able to see hopefully this process unfold in the right star. This is exactly what Patrick got.
There's a pre-predicted model called SW17, which accurately matches what you were able to observe.
And this is also one of the important bits. We've had lots of models of what is the exact process that unfolds based on the size of the star, how much stuff is there, the mass or the density, and how quickly the shock wave moves. And because previously supernova would only been caught maybe a day or two after explosion, if we're lucky, and we'd only monitor a supernova every day or two, again, because we're looking from the ground, we can't see it continuously. We have the day and night cycle and things move and our Earth moves. But because Kepler was in space staring continuously, we were able to see from within 30 minutes of detonation or that shock wave going through the star, seeing the whole unprocessed fold for 80 days. And every moment for every 80 days, we're able to say, yep, this is exactly what happens. This is the exact model that predicts or matches what we see because it's kind of unambiguous with so much data we have. And this is the process that unfolds. So now not only is it exciting to understand what happened to this particular star, but now when scientists go and find other stars, they won't have the same data really Kepler does. But they'll say, okay, well, we don't need to bother trying to figure out other models. We know this is the one that works. We're going to use that one, and it should give us a pretty accurate measurement.
And is it a case that this model works only for certain types of supernovae events?
So this really works on what we call the core collapse, these big, massive stars, 8 or more times the mass of our sun collapsing. And depending on the exact type of star, you have to tweak a little bit of the model because a red supergiant is slightly different in terms of its size and density to a yellow supergiant, the one we saw here. But still, we can then say, all right, well, we just need to adjust the parameters for a red supergiant if we expect it to be that type of supernova. So we kind of know, and we're starting to match the stars that explode and what their light curves or their explosion over time looks like, playing that matching game, and therefore use the correct model and physical measurements of the star to get the right properties. So really, it's kind of this big game of what do we see, what does it look like, what do we need to measure the star, and then what does it tell us ultimately about the life cycle and the ends of these stars.
The progenitor, what do we know about it?
So in this case, we do know that it was a yellow supergiant. So this is a star that started to rapidly expand. The outer shell, as it's called, or the photosphere, is really big. It's really puffed out. So it's a very wide star, let's say, if that's the correct way of thinking it. But also it is much heavier than the sun. In this case, this yellow supergiant was, anywhere between 10 and 14 times the mass of our sun. The radius or the width of the star was anywhere between 50 and 300 times the radius of our sun. So there's a little bit of uncertainty there, but we kind of know it has to be within that range. So we're talking about something that is much wider than the sun and quite a bit heavier.
How far away was this star?
So this star was it was a redshift of 0.07, which is about 1 billion light years away. So this actually was a relatively faint supernova, and it was on the boundary of the limits of what Kepler could successfully detect and measure. So this is actually kind of what was exciting is it was at the limits of what we could measure with Kepler, but it was still big enough and bright enough that we were able to see all this detail and in a pretty great amount of detail, if that. So it was one of the more distant stars that we've detected with Kepler. Some of the other supernovae have been in the 4 to 5 to 600 million light year range. This was just slightly over 1 billion light years away.
And you were talking about it being a yellow supergiant. That's different from a red supergiant or an orange supergiant. What makes them different?
So just as stars in our nighttime sky have different colors, it's all about the temperature, how hot they're burning. And really, how hot they're burning is related to their age and how much gas or material the star has, fusing atoms together, creating that energy. That energy comes out as heat or temperature, and that temperature glows a color. Just like in the flame of a fire, the red flame is a bit cooler than the blue flame. Same with stars. Red supergiants are cooler than yellow supergiants, which are even cooler than blue supergiants. And all of those stars we do now know can explode as supernova, but they all produce slightly different explosions because of just how much energy and how bright they can be seen.
So because this was a yellow supergiant as opposed to a red supergiant like, say, Betelgeuse, the characteristics which led to its explosion would have been slightly different.
That's exactly right. So the characteristics would have been slightly different. Therefore, the shock wave would be slightly different. And then the corresponding light curve, or the way we see the explosion happen over the consequential days to weeks, looks different as well. And again, this is one of the keys. By being able to pinpoint exactly what are those initial circumstances that actually happen and what is the best model that describes what happened, we can then apply this to a whole bunch of other supernova and understand in the future what actually is happening when these stars explode. And this is kind of the really cool thing. Just 20 years ago, there was a lot of uncertainty and knowledge about, we see all these explosions. What are the progenitor stars? What are the stars that are causing these explosions? But in the past 10 to 20 years, we've now seen a few different techniques, this one being the one. Another one being we just directly image a galaxy, see the individual stars, and then go back and look when a supernova happens and see what star was present at that location. We're now being able to match up what happens in the actual star and then how it explodes, putting together this complete, hopefully, picture of the life cycle.
That's Dr. Brad Tucker, an astronomer with the Australian National University. And this is SpaceTime. Still to come, SpaceX builds the world's biggest rocket, though only very briefly, and the long-distance pizza delivery to the International Space Station. All that and more still to come on SpaceTime. Well, it was only done to make sure everything fits, but SpaceX has briefly assembled what is the world's largest ever rocket, placing the SN20 Starship spacecraft on top of its Super Heavy booster, in the process creating a giant 122-metre tall launch vehicle, 13 metres taller than NASA's mighty Saturn V Apollo moon rocket. The two segments were connected for about an hour at SpaceX's research and development facility at Boca Chica in Texas before the two spacecraft were separated again. SpaceX plans to send the SN20 Starship test article into orbit aboard the Super Heavy on a test flight in coming months. Both segments will be ditched into the ocean following this test flight, but in the long term the company plans to develop both vehicles to be reusable. The first so-called revenue run for Starship will be a private space tourism flight to the moon and back. That's slated for 2023. Meanwhile, a lunar lander version of Starship will be used by NASA to transport crew and supplies between the Gateway Space Station and the moon's surface as part of the Artemis missions from 2024. SpaceX boss Elon Musk developed Starship as a fully reusable super heavy lift spacecraft capable of carrying 150 tons of people and cargo into orbit and 100 tons on missions to the Moon, Mars and interplanetary journeys across the solar system. Musk says he sees Starship very much as a colonial transport system. Ultimately, it'll replace the company's existing Falcon 9 and Falcon Heavy launch systems as well as its Dragon capsules. The 120-ton upper Starship stage of the launch system is 50 metres long, 9 metres wide, and powered by 6 liquid methane and oxygen propellant Raptor rocket engines, 3 designed for atmospheric flight and 3 for the vacuum of space. They'll deliver approximately 12 meganewtons or 2.6 million pounds of thrust. And Starship will be equipped with its own retractable landing gear, allowing rocket-assisted vertical landings, just like the Falcon 9 does now. Meanwhile, the 230-ton booster or first stage, called the Super Heavy, is 68 metres long and powered by 37 liquid methane and oxygen-propelled Raptor rocket engines, providing 72 meganewtons or 16 million pounds of thrust. Musk says he's also planning refueling tanker and satellite payload versions of the upper stage, resulting in the supply of a complete family of launch systems. This is SpaceTime. Still to come, NASA's long-distance pizza delivery to the International Space Station, and later in the science report, global warming reaches 1.1 degrees above pre-industrial levels. All that and more still to come on SpaceTime. Northrop Grumman's Cygnus NG-16 cargo ship has successfully docked onto the International Space Station carrying a precious cargo of pizza. The spacecraft, loaded with 3,723 kilograms of food and other supplies, had launched 2 days earlier aboard a Northrop Grumman Antares rocket from NASA's Wallops Island flight facility on the Virginian mid-Atlantic coast.
5, 4, 3, 2, 1. There's engine ignition.
Main engine start. And we have liftoff of Antares for NG-16 mission in the Wallops Flight Facility. Engines at 100%. Attitude nominal.
The SS Ellison Onizuka now on its way to the International Space Station to deliver more than 8,200 pounds of cargo. Good first stage performance so far.
EV and power subsystems are nominal. G16. All systems are nominal. Engines at 100%. Duration of stage 1 burn is approximately 3 minutes and 18 seconds. Passing through 40,000 feet. Passing max Q.
First stage now passing through the area of maximum dynamic pressure. Again, this first stage will burn for about 3 minutes and 18 seconds until main engine cutoff.
All subsystems continue to perform as expected. Passing 70,000 feet. Engines continue at 100%. Core pressures nominal. All vehicle subsystems nominal. Passing 120,000 feet. Attitude nominal. All G&C performance as expected. Throttle down to 80%.
Throttling down 3 minutes into flight, main engine cutoff coming soon.
Throttle down to 55%. All systems nominal. Stage 1 MECO.
We have main engine cutoff, Antares entering into a co-stage, standing by for stage 1 separation.
Then stage 2 ignition.
Stage 1 separation confirmed.
Antares is in coast phase. Attitude nominal. Fairing separation.
Fairing separation confirmed.
And we have stage 2 ignition. Stage 2 will burn for roughly 2 minutes and 30 seconds. All systems continue nominal.
Stage 2 ignition is confirmed. Stage 2 is that solid rocket fuel that will burn for about 2 minutes and 45 seconds. Burnout will come at 6 minutes and 52 seconds into the flight today.
Altitude approaching 140 kilometers.
Now 5 minutes into flight, everything proceeding smoothly.
Stage 2 burn continues. All systems nominal. Altitude 170 kilometers. All systems continue to perform as expected. Stage 2 burnout. All systems nominal.
And stage 2 burnout is confirmed.
Antares will coast for approximately 2 minutes till spacecraft separation. Antares is in orbit. Altitude nearly 180 kilometers. Attitude nominal. Antares continues to orient and prepare for spacecraft separation. Altitude 179 kilometers, roughly 30 seconds to spacecraft separation.
Standing by for spacecraft separation.
And we have spacecraft separation. Go Cygnus.
Spacecraft separation confirmed, and Cygnus has separated from the second stage.
Space Station crew used the orbiting outpost's robotic arm to capture the Cygnus during rendezvous and mate it to the Earth-facing Nadir port on America's Unity module. Included in the manifest are 1,396 kilograms of food and crew supplies, including fresh apples, tomatoes and kiwi fruit, along with those all-important pizzas and a cheese smorgasbord. Also aboard are 48 kilograms of unpressurized cargo, 15 kilograms of spacewalking equipment, 44 kilograms of computer resources, and 1,037 kilograms of vehicle hardware, including new mounting brackets for new solar arrays which will be delivered next year, a new carbon dioxide scrubber, a new air filtration unit, and a prototype infrared missile tracking system. Cygnus was also carrying 1,064 kilograms of scientific equipment and supplies, including materials simulating moon dust and dirt, which will be used to create items from the space station's 3D printer, hopefully leading the way to eventually using local resources on the Moon and Mars as building materials. There's also an experiment to identify drugs to treat muscle wastage, equipment demonstrating a new two-phase thermal management system for long-duration spaceflight, a new thermal protection system for spacecraft atmospheric re-entry, and The Blob, a slime mold experiment for French schoolkids. The Cygnus will remain docked to the space station until November. When it departs, its SEOP slingshot deployment system will be used to deliver a number of CubeSats into orbit before the Cygnus itself deorbits and burns up in the atmosphere. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The latest report from the Intergovernmental Panel on Climate Change warns that global warming has now reached 1.1 degrees above pre-industrial levels due to the continuing use of fossil fuels. The report found that in Australia the average temperature increase was even worse at 1.4 degrees Celsius. The IPCC report, based on over 14,000 separate scientific studies, says the planet remains on track to increase global warming by 1.5 degrees within the next 2 decades, and probably as soon as 2030. It confirmed that the changes now being observed in the planet's climate are unprecedented in thousands, if not hundreds of thousands of years. It provided evidence showing atmospheric carbon dioxide levels are now at the highest they've been in more than 2 million years. The level of glacial retreat is unmatched in the past 2,000 years. The last decade has been the warmest for some 125,000 years. Sea levels are now rising faster than at any time in the last 3,000 years. Summer Arctic ice coverage is now lower than at any time in the past 1,000 years. The oceans are warming faster than at any time since the end of the last ice age. Ocean acidification is now at its highest level in 26,000 years. And weather extremes, once considered rare or unprecedented, are becoming more common, a trend that is now destined to continue even if the world limits global warming to 1.5 degrees Celsius. The studies also confirm that heat waves, which used to only happen once every 50 years or so, are now happening roughly once every decade. Tropical cyclones are getting stronger, most land areas are seeing more rain or snowfall in a year, severe droughts are happening 1.7 times as often, and fire seasons are getting both longer and more intense. Now, for Australia, it means events such as last year's Black Summer bushfires will become more frequent, with major outbreaks occurring more often and fire seasons lasting longer. Heavy rainfall and river flooding is projected to worsen across Australia, with drier winters and fewer days of rain in the east, but heavier, more intense falls when it does rain. As global warming reaches 2 degrees Celsius, it'll cause increased drought conditions in eastern Australia, and the drought periods already prevalent in southern Australia will get worse. And local sea levels, which have already risen higher than the global average, will continue to rise, causing increased coastal erosion. The study also found that China remains the world's biggest single polluter, pumping out more greenhouse gases into the atmosphere annually than all the OECD countries combined. Beijing remains committed to increasing its coal industry while the rest of the world looks at reductions. It's now home to half of the world's coal-fired power stations, with new plants under construction and more in the planning. According to the Institute of Public Affairs, China now produces as much carbon dioxide in 16 days as Australia does in an entire year. And under the Paris Agreements, China will continue increasing its greenhouse gas emissions until at least 2030. At the moment, China is increasing the amount of greenhouse gases it produces every year by an amount already greater than Australia's total yearly output. Meanwhile, authorities in Sicily have seen what may be the highest temperature ever recorded in Europe, 48.8 degrees Celsius. That's 120 degrees Fahrenheit on the old scale. Now, if confirmed, it would break the old record of 48.5 degrees, also set in Sicily. Similar temperatures have been recorded in Greece, Tunisia and Libya as a Mediterranean heat dome named Lucifer continues to bake the region, triggering some of the area's worst wildfires in recorded history. It follows similar extreme heat waves across the western United States and Canada last month, and in Australia in the southern hemisphere summer, which saw temperatures in the Australian outback reach 48 degrees Celsius. A new study finds that people who've already been infected with the COVID-19 coronavirus and are then given a single dose of the Pfizer vaccine tend to produce higher antibody levels than those who've never been infected and get 2 jabs. The findings, reported in the Journal of the American Medical Association, also showed that previously infected people with a good immune response after the first dose didn't get any additional immune response from a second jab. The findings suggest that for people who've already had COVID-19, a single vaccine dose may be enough. The World Health Organization estimates that more than 8 million people have been killed by the COVID-19 coronavirus, with over 4.4 million confirmed fatalities and more than 205 million people infected since the deadly disease was first spread from Wuhan in China. Paleontologists have discovered what might have been Australia's largest ever flying reptile, an ancient pterosaur that once soared like a dragon above a vast inland sea which once covered much of outback Queensland. The discovery, reported in the journal Vertebrate Paleontology, has been named Tarumgaga shorai. The pterosaur, which flew the ancient Australian skies some 110 million years ago, had a metre-long skull with a spear-like mouth containing some 40 teeth, a bony crest on its lower jaw, and a wingspan of around 7 metres. Its fossils were uncovered in a quarry near Richmond in northwestern Queensland. Scientists have discovered the oldest known example of applied geometry. A report in the journal Foundations of Science says that 3,700-year-old Babylonian clay tablet known as SI427 appears to provide the legal and geometric details of a field that was split in two after part of it was sold off by its Babylonian owner. The surveyors used what are now known as Pythagorean triples to make accurate right angles and define the new land boundaries. The tablet was originally discovered by a French archaeological expedition in central Iraq back in 1894, but was simply catalogued and stored with other artefacts. Its true significance was eventually uncovered by mathematician Daniel Mansfield from the University of New South Wales. Well, it seems obvious, but a new study from the Netherlands has shown that despite how analytical you may try to be, your underlying beliefs will still surface to affect how you see things. The findings help explain things like Nobel disease, the hypothesized affliction that results in some Nobel Prize winners embracing strange and scientifically unsound ideas, usually later in life. Tim Mendham from Australian Skeptics says the study, reported in the Skeptics magazine, helps explain why even the most intelligent people can still choose to believe nonsense.
There are suggestions as to why people believe certain things, and some of the stuff in this, I was looking closely at this paper from the Netherlands, and I think it's the University of Amsterdam or something like that, and really some of the things it was saying was pretty inane, quite frankly. There's different motivations for why people believe different things, and really? That there's political motivations for believing some stuff, and there's religious motivations for believing in other things, and the suggestion is that why aren't people following the science is because of these underlying motivations, which are not necessarily scientific. For instance, they were saying that spirituality, by which they don't mean religiosity, but they mean sort of really could almost like belief in woo, as we say, paranormal or hippiedom or new ageism or belief systems anyway that aren't necessarily straight religion beliefs. They would have a higher rejection of scientific evidence than some who are less spiritual. But to me, that's almost stating the obvious, that people who reject science. Yep, really? Yeah, yep, okay, I can accept that. Why do they reject science? Because some people just don't believe scientists. As one radio reporter once said to me, on the ABC actually, and they said to me that, scientists are evil because they invented the bomb. And as I pointed out, well, most scientists didn't actually invent the bomb. In fact, the vast majority of scientists didn't work on the bomb.
Was that reporter simply giving an opinion, or was he?
It was a very much a hippie-like sort of response. Someone who's spiritual, who's just
and your
blanket,
taxes are paying for that person to actually work there. There, oh dear.
But I know they were said that, and they were saying that whales are more intelligent than people. And as I pointed out, well, the whales didn't invent the bomb either. Some people's beliefs are pretty sort of let's say superficial. But the reasons
jobs at the ABC.
Sort of the reasons why people believe are many and varied depending on the belief. And some of the stuff that was in this paper was to me a bit light on. But you can say quite readily there are different reasons for different people's beliefs. Religion comes into it, politics comes into it, spirituality comes into it. Preferences for lifestyle preferences for what you want to do and what you want to be true and all the reasons behind those things. are all influences on how much you believe science, apart from pure evidence. Obviously, skeptics would like to say their beliefs are all based on pure reason and logic and whatever, but I mean, everybody is biased in one way or another, and everybody, even the most scientific of brains, can be influenced by other factors. And of course,
but isn't the art learning how to distinguish facts from bias and then focusing on the facts only? Isn't that what good journalism's all about?
That's what it should be all about. Yeah, it's critical thinking, right? That's the term for it. You're just using your brain to actually look at the evidence or whatever, or the claims that are put forward from as independent a point of view as you can, but obviously being a journalist or having a supposedly analytical mind or being a scientist was supposed to be very much an analytical mind is no guarantee. You might be trying to be not biased in your science, and even scientists themselves can have strange beliefs in other areas.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.